Hi, this lesson is about the real zeros of a polynomial. So what are zeros? Zeros are also called roots or x-intercepts. These answers can be rational or irrational numbers, but they do have to be real numbers to be a solution or a root or an x-intercept. The rational root theorem states that if you have a polynomial p of x, which is a sub n to the x times x to the n plus a sub n minus 1 times x to the n minus 1, etc., all the way up to a sub 0, and it has integer coefficients. So a sub n through a sub 1 are integer coefficients, where a sub n is not equal to 0 and neither is a sub 0. Then every rational number of p is in the form of p over q. Now, what are p and q? P and q have to be integers, and p are the factors of the constant, which is the a sub 0. And remember what a factor is. It's a number that will divide evenly into another number. So if I said, what are the factors of 6? Your answer would be 1, 2, 3, and 6. So that's what they mean by the factors of a number. And q is a factor of the leading coefficient of a sub n. So whatever this number is, whatever those factors are, and the combination of fractions that can be created from the factors of a sub 0 over a sub n is what your potential zeros or roots of your polynomial can be. And that's only if you get if you have real number answers. We know that sometimes you can get imaginary or complex numbers that would not be found via this theorem. Okay, so we're going to use the rational rational zeros theorem to find the rational zeros of p of x, where p of x is x to the third minus 3x plus 2. So the factors of p would be the factors of my constant 2, and those numbers are going to be plus or minus 1 or plus or minus 2. Always consider the positive or the negative numbers as possible factors, because a negative number will divide into 2 just like a positive number would. And your factors of the leading coefficient of x cubed, which is 1, well, that's just going to be plus or minus 1. So if I look at the combination of possible numbers created by p over q, that could be 1 over plus or minus 1 over plus or minus 1, or it could be plus or minus 2 over plus or minus 1. So it's basically these possible four numbers. So either positive 1, negative 1, positive 2, or negative 2 are potential zeros of this polynomial. Now, how do we know for sure if it's a zero? One way is to check by just plugging in the numbers. So if I plug in any one of these four numbers into my original function, and if the answer for p of that number is 0, then you have found an actual zero or root for your polynomial. So when I plug in negative 1 and resolve it, I get 4. So negative 1 is not a zero of the polynomial. When I plug in positive 1, that does work out to be 0. So 1 is definitely a zero of the polynomial. When I plug in negative 2, I get 0 again. So therefore, I have two zeros of the polynomial. And when I plug in 2, I get 4 again. So the rational zeros of p of x are negative 2 and positive 1. Not every polynomial will have rational zeros. Some will have complex, only complex. That's possible. So in this case, we have found two rational zeros using this method of looking for the ratio of the factors and plugging them in and seeing which one give me a result of 0. But there is more than one way to determine if a possible zero or a root of a polynomial is an actual zero or root of the polynomial, and that is to use synthetic division. If the remainder is 0, then the possible root is an actual root or an x-intercept of the polynomial. So synthetic division is usually a pretty quick process. And if you get a remainder of 0, then you have found your answer or your root. So here I have another polynomial. I have 2x to the third plus x squared minus 13x plus 6. So the factors of my constant are going to be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. The factors of the leading coefficient are plus or minus 1 and plus or minus 2. So my potential ratios of P over Q are going to be, so you have to first take each of these and put them over 1 with plus or minus 1, which means it's basically this initial list first. And then you take all of these numbers and put them over plus or minus 2. Some of them will be repeated, but I get a couple of unique ones, which are plus or minus a half or plus or minus 3 halves. Those are all of your potential rational zeros of this polynomial. So there's a lot more than I had before. So finding a quick way to figure out if any of them are roots is really helpful. So I showed you a few here and list and do a synthetic division for every single one of these. But here I showed you synthetic division using -1. And when I do all that work, I end up with a remainder of 18. So -1 is not a possibility. And then I did it with -2 and I got a remainder of 20. So that one doesn't work. Remember, we talked about synthetic division in a previous lesson. So you can go back to that if you don't remember how to do synthetic division. When I check 1, I get -4 as a remainder. So 1 is not a rational zero. When I check 2, I get a remainder of 0. And this means that 2 is a root of the polynomial, which means the factor x minus 2 divides into the polynomial evenly. And if that's the case, then I can rewrite the original polynomial as a product. So this is going to get rewritten as x minus 2 times, and then here's my quadratic, 2x squared plus 5x minus 3. And the reason why that's helpful is because now I can take that quadratic and factor it and be able to find the other roots more easily than having to go through this entire list. So when I factor it, I get 2x minus 1 times x minus 3, which means that the three roots of this third degree polynomial are x equal to 2, x equal to a half, and x equal to -3. And now I have found the complete set of all of the roots of the polynomial. And the reason why I know I found them all is because I cannot have more roots than what the degree is. So you're not going to find more than 3 roots for a polynomial. It is possible to find less than 3 real number roots, but in this case, they're all real numbers. Okay, so here I have another one. I have p of x is equal to x to the fourth minus 3x to the third minus 6x plus 8. So again, I'm going to list all of the possible roots of my constant, which is plus or minus 1, plus or minus 2, plus or minus 4, or plus or minus 8. And my leading coefficient here is again 1, so that makes things a little easier. Roots, the q roots are just plus or minus 1, which means that the ratio of p over q is just the same list that I had just for p. So that's what I need to check. And so again, I'll use synthetic division. So here's the work for the number 1, and I have found my root. So when I rewrite this in a different way, I get x minus 1 times, and then all of this gets rewritten as x to the third minus 2x squared minus 2x minus 8. So x equal to 1 is right here. So this is a piece of the graph. The graph was rather big to show. So it does continue on down in this area here. But when it comes back up, it intersects the x-axis again right here. And that is a real number, but it's not a rational number. It can't be set up as a fraction. So we have found that this one also has an irrational root, which would not be found with this theorem. So the graph allows us to see that we have two roots here, two real number roots, but only one of them is a rational number, which is x equal to 1. Okay, so here we want to list all the possible roots or possible zeros, rational zeros for p of x equal to x to the third minus 19x minus 30. Then we're going to determine which ones are actual zeros. So the possible zeros are going to be all the factors of 30. Leading coefficient here is 1, so that's not really going to change anything. So my list is here: plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, and plus or minus 30. A good way to make sure you're not missing any is that all of these should be paired off. So 1 and 30, 1 times 30 is 30, 2 times 15 is 30, 3 times 10 is 30, 5 times 6 is 30. So that way you're sure that you haven't missed any of the possible roots. So, so I used a graphing app to put this into a graph. And according to what I see on the graph, it looks like it intersects the x-axis at -3, -2, and at 5. Now, the only way to know for sure if those are actual zeros of your polynomial is to do our check. And so I'm going to use the check of synthetic division. I'm going to check -3, -2, and 5 and divide it into this polynomial. And if my remainder is 0, then I'm sure that the graph is correct. And that, again, saves quite a bit of time rather than checking every single one of these, which is a rather long list. So when I do my synthetic division for -2, I do get my remainder of 0. Synthetic division for -3, I also get a remainder of 0. When I check 5, I also get a remainder of 0. So you can say with confidence that the zeros of this polynomial, or the rational zeros, are -3, -2, and 5. Now, part B of this problem says to write the polynomial in factored form. What that means is that you have to write each of these answers here in terms of its corresponding factor. So x minus 3 corresponds with the factor of x plus 3. X -2 corresponds with the factor of x plus 2. And x equal to 5 corresponds with a factor of x minus 5. If you were to multiply this out, it would equal the original polynomial that we started with, the x to the third way up here. Okay, so a graphing app helps to focus on what it is that you should be checking. That's especially helpful when you have a very long list like this was. Okay, so here's one for you to try. List all possible zeros for t of x equal to 4x to the fourth minus 2x to the second minus 7. So again, you're going to want to find all the factors for 7, all the factors for 4, and then write that as a ratio in terms of what the possible rational zeros will be for t of x. So you can give that a try. Good luck.